Now that we've studied electric fields, now we're going to look at motion in electric fields. We're skipping ahead to 22.8 to 22.9, and then we'll go back and take a look at some other electric fields, and we'll fill in that electric field chart you have a little more. So first of all, recall gravity. That first slide, all we're really doing is illustrating this. If we look at the Earth, near the surface of the Earth, right, near the Earth's surface of the Earth, we consider the gravitational field to be relatively uniform. And then as you get further away, then the field starts changing in strength. But as long as you're very close to the Earth, it's about the same, which is why in potential energy, as long as you're close to the surface of the Earth, we can just use mgh instead of the whole G/m/m/r formula. And so we're going to be looking at that in a similar way with electric fields. So first of all, a uniform electric field due to some outside source. Okay, so we have some electric field, and let's say that the electric field is up. So if we have that big box that you've got on the page, so if the electric field is up, and we can represent that with a line or an arrow with an E next to it. So this arrow represents the electric field. If I have some positive charge on it, some positively charged object, what are the forces on this? Well, up, you have the electric force, which is equal to EQ. Right, the electric field times the charge of that object, and you've got mg, the force of gravity pulling down, and you can suspend some object that way. That's the famous oil drop experiment that Millikan did. It's that kind of thing. They had oil drops, and then they were able to see when a charge jumped off how far it fell, and they were able to calculate the charge on an electron that way. Brilliant, beautiful experiment that they did. And then if we have a negative charge, then the electric field force and the gravitational force are both downward. Right? And if the E field points down, right, so we have some outside source producing an electric field, a positive charge, the electric field force is going to be down, and the gravitational force is going to be down. But if we have a negatively charged object, then the electric field force is going to be up, and the force due to gravity will be down. Okay, so under what conditions will a positively charged object be suspended? When you have an upward electric field. And when will something that's negative be suspended? When you have a downward electric field. A lot of the electric fields we're going to be looking at, we're going to assume that they're produced by charged plates, charged parallel plates, a positive and a negatively charged plate. And remember, the electric field always points from the positive to the negative. But if we have these parallel plates like this, then it's relatively uniform. Kind of like how we had relative uniformity near the surface of the Earth. When we get to the outside, we end up with, in reality, this effect called fringing. For the most part, we're going to ignore fringing, but in reality, it is there. So for now, we're just going to simplify things a bit. And our electric fields are going to look uniform in a lot of the examples that we do. So the first one, imagine we have, so this one's like this. Okay, so the electric field, assume that it's uniform. I'm going to put an E here so you know these arrows are the electric field. Over here, this one next to it, we flip the electric field. So this is negative, positive. That's the electric field that way. If I have some positively charged object come into this, what's that going to look like? Well, I have the electric field force, right? Fe equals EQ. And if it's shot this way, it's going to go down. And, what does this look like? It looks like projectile motion. And so what's the acceleration? The acceleration is just going to be EQ over m. That's the downward acceleration of this, we could say. And this is for when the electric field force is much greater than mg. If the force due to gravity is a lot less than this, then we can ignore this. But if it's not much smaller, then we can include that. And now we have two forces acting on this, right? The electric field force and the gravitational force. This would work the same way here, but if we have a negatively charged object, right? Because the negatively charged object is going to be pulled towards the positive plate. All right. And the next slide, what exactly is this path going to look like? If this is positive or this is negative, if I have some positively charged particle here, is it going to hit this plate? Is it going to hit this plate? Or what, is it going to pass all the way through? Well, with a large velocity and an angle here, it might hit that plate. Or if it's shot at just the right speed and angle, it might make it through. Or, not enough speed, maybe it'll hit this plate. So the exact trajectory depends on the numbers. Depends on the strength of the force. It depends on the initial velocity and the angle. Just like when dealing with projectile motion. Right? So same kind of thing. Okay, so now imagine that we've got two parallel plates, and each, so this is two separate cases here. And we've got some positive charge that's going to be shot through a little hole here, and then we're in an electric field. Let's say it's a uniform electric field, looking something like this. All right, and what's going to happen here? Well, when it passes through here, this one's going to speed up. Once it gets here, it's being pushed that way by this force, and so it's going to speed up. And again, this can be a little weird because we're like, oh, we're dealing with electric charges now. It's still just forces. Forces, and we have mass, right? The acceleration is going to be proportional to the force and inversely proportional to the mass. Same kind of thing as before. It's just now we're dealing with an electric force, and the way we calculate the electric field is a little different from the way that we calculated the gravitational field. Okay, so don't freak out, just keep the basics in mind. Specifically Newton's second law, right? F equals ma, everything. And so then in this case, if I have a positively charged object shot into here, now the electric field is pointing in the opposite direction. Right? Electric field tells us the force on a positive charge. So once it's shot in here, it's going to slow down because there's a force on it that way now. And it might, if it's going fast enough, it'll hit this plate. If it's not going fast enough, it might stop and then come back out. We don't really know. But here it is going to slow down. Okay. Now let's consider this whole thing again. Same setup really, except that we're going to have a negative charge. Right? This makes sense. If it's negative, it's going to come in here. But now the electric field's pointing that way, which is the opposite direction that a force would be on a negatively charged object. And so it goes this way, and then it's going to slow down once it's in this field because the force is going to be that way. So here it's going to slow down. It might stop, it might not. It might hit that plate, might come back out. We don't know. And then here, a negatively charged object would come in, and it's going to be repelled by this plate and attracted to the positive plate. So here, a negatively charged object would speed up through this electric field. All right. So let's take a look at some examples of this now. Example number 1, we have this situation, right? Let me go over here. Positively charged plate here and a negatively charged plate here. That means I have an electric field going this way, right? So the first question is which plate is positive, which is negative. Since the electric field is going this way, we know this has to be positive, this has to be negative, right? And then we want to know find VF and its change in kinetic energy after it has moved a distance x. So we've got this object in here. They tell us that it's a proton. And so for part B, we know that VF squared equals VI squared plus 2A delta x, right? It's not given to us in terms of time. They're not telling us that. They want to know it in terms of a distance x. And so we can do it this way. Initial velocity is 0. And so VF is the square root of 2A delta x, at some distance x. And so then we want to know the change in kinetic energy. Well, delta K is going to be Kf minus Ki. Ki is 0 because it starts off at rest. So then Kf is going to be 1/2 mv squared. So it's going to be 1/2 the mass of the proton times 2a delta x. The 2's cancel out. So the mass of the proton times the acceleration times delta x. But we can also see, right, the acceleration is going to be the force of the electric field over the mass of the proton, right? F equals ma. And so these cancel out times delta x. So the change in kinetic energy is F delta x. Right? And that's going to come into play later when we talk about voltage, right? Potential energy and that sort of thing. So interesting result that we get there. Now letter C, what work was done on the charge by the field. So C, again, the change in kinetic energy is, it would be this, right, Fe. Well, how do we get Fe? Fe is the electric field times the charge, EQ. But let's see how that turns out this way. Let's try this. Work is the integral F dx, right? But the force is EQ, and dx is the distance that it goes, so it ends up being EQ delta x. It's a uniform electric field, so we don't have a function there, and so that's the result we get. Same kind of thing, same thing that we got here. And can gravitational effects be neglected? Yes, because if you calculate this EQ, it's much, much greater than mg. Right? We don't actually have numbers here, but we're assuming. Okay, so now let's take a look at, all right, and so let's take a look at A, calculate the initial speed of the electrons. So we know what the kinetic energy is, and so for part A, K is 1/2 mv squared, so V is going to be the square root of 2k over m. Now we plug in 1.6 times 10 to the negative 17th and the mass of an electron, and we end up with 5.93 times 10 to the 6th meters per second. Okay, so moving pretty fast. And then part B, we want to know what is the acceleration required to stop the electrons in a distance of 10 centimeters. All right, so this, again, A is going to be EQ over m. This is the force of the electric field on that charge, and this is the mass of the object. And again, we're doing this in terms of a distance x, so we're going to use the VF squared equation, right? So VF squared is VI squared plus 2a delta x. VF squared is 0, and this we're going to plug in here for A. Or rather, we're looking for A. Oh, and we have VI and we have delta x, so we're not going to plug that in. Never mind. But that'll come in later. And so, since we have A is going to be, let's see, negative VI squared over 2 delta x. And so we plug in our numbers. Delta x is 0.1. VI squared was that same initial, or this initial velocity, which we calculated. And so we end up now with negative 1.7 times 10 to the negative 14th meters per second squared. Notice this is negative because it's going to be slowing down a positive velocity. Now we want to know, C, draw a simple sketch of the situation. Here it is. I already kind of started it. If we want to slow it down, that means we're going to have the positive charge here, negative here. So the electric field's going this way. And the electron is coming in here, so it'll slow down when the electric field is pointed to the right. And now for part D, we want to know what is the magnitude and direction of the E field required. Well, from this, A equals EQ over M. We can solve it for E, because we know A, Q, and M now. So the electric field is AM over Q. And so we plug in our numbers. right? The acceleration is what we found here. That's what that is. The mass of the electron, 9.11 times 10 to the negative 31st kilograms, and then the charge on electron, 1.6 times 10 to the negative 19th coulombs. We plug those numbers in, and we end up with 968 newtons per coulomb. Again, those are the units on electric field. And we'd see the electric field then has to be pointing to the right. So can include that there. Part E. Now we want to know the force required to stop the electrons. So E, the force, is high. All right, so the force of the electric field is going to be the electric field times the charge on the object. The electric field we just calculated, and the charge on the electron is 1.6 times 10 to the negative 19th coulombs. And so that ends up, you plug that in, you get 1.5 times 10 to the negative 16th newtons. Another way of doing that would simply to have been multiply the mass of the electron times this acceleration, and it'll give you that, that force. This, of course, is the magnitude. The direction would be negative to the left. Okay, example 3. Electron enters a uniform electric field as shown, so now this is coming in sideways, kind of like a projectile launched horizontally. And they give us the electric field intensity, 200 newtons per coulomb directed upwards, as it is in the diagram. And they tell us the initial velocity of the electron. The width of each plate is 0.1 meters, so that's how long it is sideways. And then we want to know, are the plates sufficiently we know that they're sufficiently separated, so the electron's not going to hit the plates. So now calculate A, the acceleration of the electron while it's in the field. So again, we know F equals ma. This is EQ. So A is going to be EQ over m. Right? So the electric field is 200. The charge on an electron and the mass of an electron, and so we end up with this 3.5 times 10 to the 13th meters per second squared in the downward direction. Okay, next, the time required to travel the horizontal distance of 10 centimeters. B. Remember, the horizontal velocity is not going to be affected by the vertical force, just like with projectiles. And so all we care about here, delta x is vt, or t is delta x over v. And so delta x is the 0.1, v is the 3 times 10 to the 6th meters per second. We end up with 3.3 times 10 to the negative, what does that say, 8th seconds, or 33.3 nanoseconds. Right, if we move it over one more time, that's 10 to the negative 9th, it's a nanoseconds. And so now the vertical displacement. Well, how do we calculate vertical displacement? That's going to be delta y, or h, right? VIYT plus 1/2 AT squared. This is actually kind of refreshing to be doing some, just seems like regular VIFTAD, right? But now we're dealing with electricity. Don't get freaked out. This is still the same kind of stuff that we've done. VIY is 0. So all we're doing is plugging in 1/2 A. This is the acceleration we found, and this is the time that we found. Plug this in for A, this in for T, and when you do that, that's just calculator work, you should get 0.159 meters. Okay, and we're assuming that the plates are separated more than that, so it does pass through and go out the other side. So let me move over here a little bit. So for part D, we want to know the electron's velocity as it leaves the field, and so we're going to look now at VFY. We know what the horizontal velocity is. That's not changing. But the vertical velocity is going to be different now. So VFY equals VIY plus AT. This is 0. The acceleration is what we found here, and the time is what we found here. So just this times this, and that gives us the downward velocity. And we end up with 1.17 times 10 to the 6th meters per second. And so the idea here is now we have a vector, right? This is 3 times 10 to the 6th. This downward is 1.17 times 10 to the 6th. And so we use Pythagorean theorem and inverse tangent to get the angle. Right, we'll get this angle here, theta. And when you do Pythagorean theorem, I think you get 3.2 times 10 to the 6th. And the angle is negative 21.3 degrees. That's it. So that's part D. E, what would happen if the plates were only 1.5 centimeters apart? Well, since this is how far it goes, 1.5 centimeters would be 0.015. It would hit the bottom plate, plain and simple. And then for part F, which plate is positive, which plate is negative? The positive plate has to be the bottom. The negative plate has to be the top because the electric field goes from positive to negative. And, oh yeah, so this, dipole in a uniform electric field. This question actually, or question about like this actually showed up on a science league test. So if we have a dipole, remember same charge and there's a distance between them, what is the dipole, what's the torque that this experiences due to the forces? Well, the electric field is pulling this one this way, right? This has a force on it that way, and this one is being pulled that way, so this one has a force on it that way. What's going to happen is this is going to accelerate until it gets to here, and then once it turns here, then it's going to stop again, right? Because then the forces will be pulling, this one will be pulling that way, and then it'll end up oscillating back and forth. And so this is Tx, or F, times, this distance from here to here, right, that horizontal distance, which is x sine, where x is the distance right from here to there, plus fd minus x sine theta, so wherever the pole is. Don't forget that we have that dipole moment formula, QD, and so F is EQ, but it's also equal to, right, because Q is P over D, or rather P over Q gives you that distance, and so we end up with this formula PE sine of theta, right? And now for this second one where it's talking about the potential energy, there I think we should consider this the angle theta, not like it has there, because it's going to have the smallest potential energy when it's here, right? When it's in this type of position, and that's where theta will be 90 degrees, and that's where you get cosine of 90 being 0. So U is going to be potential energy given by QDE cosine theta of this angle here. Okay. And that's it for this lesson.